So, what's a vector value function? A function has an input that gives you an output. Right? A vector value function is something that takes one real value, takes a real number, and it gives you back a vector. So here's an example. F of t, and since the resulting is a vector, usually you want to do something like this. F of t is, say, t plus 1, 2t, t cubed, something like this. That will be a vector valued function because it takes a single number and it gives you back three numbers, which makes up a vector. Okay? For example, if you plug in 1, it's going to give me 1 plus 1 is 2, 1 times 2 is 2, 1 cubed is 1. If I plug in 2, it's going to give you 3, 2 times 2 is 4, 2 cubed is 8. So that's what a vector valued function is. It gives you plug in a number, it gives you back a function. Now the example of a vector valued function in physics is when you have a position vector of a moving particle. Think about the following. Let's say there's a moving particle whose position at time t is given by 2t t squared plus 2t and negative t, something like this. It's going to be moving in a plane, and the meaning of this vector is that when you put this vector is beginning point, initial point at the origin, the terminal point indicates the point where this particle is at. Okay? What can we do with such a function? We can find the derivative, right? Because the derivative of the position gives you what?
Velocity.
Velocity, right? So if you differentiate, it's going to give you the velocity, 2 comma 2t plus 2, negative 3t squared. Now if you differentiate velocity, what do you get?
Acceleration.
Acceleration. So you can get acceleration by differentiating it again, which is 0 to negative 16. You can do the opposite too. You can integrate at to get vt. Integrate. That's also possible. So when you have vector valued functions, you can differentiate and integrate just like how you differentiate and integrate single valued functions. Okay? You just have to do 3 of them at the same time. Okay? Now the velocity itself has an additional meaning, because if you think about what this is, so imagine a trajectory in 3D. I don't even know what the shape of this thing looks like, but let's just say it's some kind of a curve. At a point, if it's moving this way, where would the velocity point to? At this point? Huh? It will be tangent to the curve and go in the direction where the point is moving, right? So there's a geometric meaning to the position and the velocity. This is how you think of it geometrically. So first, the graph of the vector valued function should be thought as a curve in 3D. Okay? Some moving point, so it has a trajectory, which gives you a curve. And the derivative gives you the tangent vector. Okay? And therefore, if you have a curve in 3D, you can use the derivative of the vector valued function to come up with the line equation for the tangent line at any point. Okay. So let's think about the following question. Example, find the equation of the tangent line at t equals to 2. Let's think about that for this given RT. Okay? All right, solution. In order to come up with the line equation, you need two things. What are those two things?
Position.
Position. You need a point on the line. Point on the line. 1 point. You need at least 1 point. And then what else?
Direction.
You need the direction. Okay. The direction will be given by our velocity vector. Okay? And so let's use it. V of t should be the direction. Vt evaluated at 2 gives you 2 comma 4 plus 2 is 6. 2 squared is 4. That's negative 12. That's the velocity. And the position when t is 2, when I plug in 2 to the original, it's 4 comma, let's see, 4 plus 4, that's 8, comma negative 8. That's where the particle is. 4 comma 8 comma negative 8 is where the particle is when t is equals to 2. Let's say seconds, 2 seconds. It's right here. So we are looking for a line which passes 4 comma 8 comma negative 8 and has the direction 2 comma 6 comma negative 12. What's the line equation then? Line equation is x, y, z equal.
AB minus x1 plus x1.
Yeah, so it'll be something t plus something t plus something t plus something. This is the direction, right? And you put what? 2, 6, negative 12 here. 2, 6, negative 12. And then for the position, what do you put? 4, 8, negative 8. 4, 8, negative 8. So here you have it. You have the equation of the tangent line. Now, an interesting thing you can do is to check whether such a method will give you the same answer for two-dimensional curves. See, for three-dimensional curves, you can't do it in Calculus 1 methods, but for 2 dimensions, Calculus 1 does have some method to treat it, right? So let's think of a very simple example. Say you have another example. Example 2 will be, let's say you have y equals x squared. You can parameterize this by setting x equals to t, and y would be what? If I say x is t, what's y?
T squared.
T squared. Right? So that your vector valued function can be written as it's x comma y, right? So you have t comma t squared. Right. And then let's now come up with the question, tangent line at t equal to 1. That's a question that can be answered in both Calculus 1 and also this new thing. Okay? So solution. First, r evaluated at t equal to 1 gives you 1 comma 1. So that's where the point is when t is equal to 1. And now to get the direction, what do? Take the derivative, which is 1 comma 2t, because if you differentiate t, it's 1. T squared differentiates to 2t. And you plug in 1, which gives you 1 comma 2. And now we are ready to write down the equation, x and y. The direction, direction vector is 1, 2, so it's 1, 2, t, t. And then the position, a point on the tangent line is 1, 1, so you put 1, 1. And that's it. You have t plus 1, 2t plus 1, and then let's see. Your answer is simply just t equals to t plus 1, x equals to t plus 1, and y equals to 2t plus 1. All right, now think about how you would solve this in traditional way, or calculus 1 way. All these math were developed in more than 100 years ago, so they're all traditional. But in calculus 1 way, how would you find the answer? Well, you would differentiate. Y prime gives you 2x. And because when t is equal to 1, that gives you x as 1 and y as 1. Your y prime, when x is 1, gives you 2 times 1, which is 2. So it has a slope of 2 at 1, 1. What do you do now? You use the point slope form. Y minus y naught, m times x minus x naught, where m is now 2, and x1 and y1 is this. And then you can further simplify this and get your answer, right? Now, how would we compare this one with that one? How do you know that these are the same thing? Yeah?
Set them equal, like you would bring the 1 over from the y side, and then with the x too. Like
You would solve for t. You would solve both of them equal for t, and then since they're both equal to t, then you can set them equal to each other. So subtract 1, and you get t equals to x minus 1, if you subtract 1. And if you subtract 1, you get 2t equals to y minus 1, but then you have to divide by 2 in order to solve for t. And since they're now both equal to t, I can set them equal to each other, and we get x minus 1 equals to y minus 1 over t. Now, do you see that these are the same thing? They're the same, because if you multiply by 2, you get the same exact thing, right? This is saying exactly the same thing as that one. Okay? So we do see that in both methods, you get the equation of the tangent line. And since it works in 2D, now we can be confident that it should work for 3D. Now, if you're given this question in 2D, unless it's hard to come up with the unparametrized version, you would rather do it this way, right? But when it comes to 3D, you're really stuck with the method of using the vector valued functions.